So this is the first example, this and the first example. And the second example is very similar. The substantial difference is that we will use external mesher. So this is real topography from the Norway, and this mesh was created by one postdoc in our group, Onat Garti, which is really expert on building the mesh. He knows everything about how to create mesh using Qubit and other external packages. But it's still the simple mesh, simple model. So you see, because of the, again, computational resources, now you see the topography is not flat, and it's not like a regular mesh we saw before. And the elevation is relatively big for these horizontal dimensions. So it's probably better to use Qubit or Gmesh in this case for this type of the models. And this is a nice thing about SPECFEM, that there is such option. So slightly increased vertical scale, but this is the model. We have in this example only 2 layers. Low velocity and high velocity at depth. So you can see some vertical slices of the mesh. Yeah. I think so. Where the model, the topography is complex, I think the better way would be used to use external mesher Qubit.
You showed this morning that, was it Columbia? Or?
Yeah, Columbia.
That was very extreme.
I spent a lot of days on tuning like parameters where you need to put the buffer layer, how much smoothing you want to apply for this interface, and like you need to guide the internal mesher. It's in a way you need try and see the output of the mesh, and I did many trials in order to build this mesh. A lot of efforts. Once you pass through this process, I think the next will be easier, but for the first time it was complicated. Okay, so how we run the mesh from the external mesher, explained in the instructions. We go to the second directory, x2 external. I think it should contain everything already. Oh, so we have the mesh folder now, and this mesh I showed you from Norway is exported from the Qubit in the .e format. So this is the mesh built in the Qubit, this file, one single file. There are a few additional programs, string, manip, and trellis to SPECFEM, which are required to convert this mesh to the SPECFEM3D. Given the instructions, you compile this C code and run. So let's do it.
What are the requirements of your Qubit mesh so that program works?
What are requirements of Qubit?
Yeah,
I think you need to build the mesh hexaedral.
Well, but you have to mark the boundaries.
Yes, yes. So I thought, yeah, it's a good point actually. So previously we had a workshop where we explained how to use Qubit to build the mesh for SPECFEM, and I thought it's also the case here, but of course it is not. You use SPECFEM, probably you learn how to use Qubit here, but not the transition. So you're right. There is a one thing you need to be aware. You need to specify the boundaries, boundary conditions. You have 6 edges, 6 faces of the model in 3D. You need create boundaries and say this is boundary 1, 2, number them. Just give the name in the qubit.
That doesn't look like it's in the manual. The manual talks about a Python script for converting, and I know that's late.
Yeah, I try to explain you why I didn't put this information, but if you, well, I don't know, I can send.
Yeah, can you provide?
Yes, we have the guidance how to like this at this point. That's what I try to say. Just you need to number the observing boundaries in the qubit. Give the name to the faces of your model, which then will be converted in SPECFEM using these commands. And yeah, this is important point. Yeah, probably I have on my laptop here, so I can.
Yeah, if you could add that to the distribution. And
Yes.
Yes.
So we convert the mesh. Now you see the files for 5 observing boundaries and 1 for the free surface. Basically, this only thing you need to be aware again in qubit. You need to name these files. Doesn't matter, like the exact names should not be the same, but I think it should be 1, 2, 3 to 6. So you have, after you run this command, trace to SPECFEM, you will have these boundary and free surface interfaces. And there is a num file for velocity, for the parameter file. So it's too many things open. So here we specify the model. It's very simple, as you saw. It's only 2 layers here. So we specify this the values for each layer. VP. So this is density. This is density. VPVS, I think. No, yeah, density VPVS. So some comments are below. In addition, I think we can use with this external mesh, we can use STOMO file. Again, as the previous, like to specify the parameters. So here is only 2 layers. It's simple. But we can use the previous approach where the SPECFEM will interpolate velocities on the given mesh. I think it's possible. So now the workflow is slightly different. We need to decompose the mesh. This is the first step. So we have this already. We decompose the mesh using this command on 16 cores. So I'm in the wrong directory. We should go back to the working directory, which contains binary, data, and mesh file, and execute the same. Okay, I didn't copy the binary folder, so I copy from the previous example to here. Now everything is there. The binary folder should be inside the working directory of SPECFEM. And if you do the same, stop error file, open database. Okay, now the problem is because I do not follow very carefully the instruction, we need to again to create the output folder. I missed this step basically. So we need to create output files folder for output and output files database MPI folder. Now let's try again one more time. Third time should be good. Finished successfully. So we decompose the mesh. We can check database folder, and you have number of files, 16 files inside this. So this step 2, and the third step is the same. We generate databases. All commands should be run through the working directory of SPECFEM. So I was there already, and we run this command. Now we don't have scripts, so we need to copy the scripts also from the previous example. I think on the virtual machine it's complete here because we used git clone and not everything copied. So like the binaries are not there because you will use binary of your system, but the scripts should be there. So we copy the scripts from the previous example. Remove the output information. And let's try to submit in the same way as we did before, databases, to generate databases. So the job is submitted. And let's look at so there is a measure. Done. If it's done, you're happy. It's because it's very often something is going wrong at the initial stages, and you need to look at this output, at which line, at which point the measure is failed or the solver is failed. You need to, well, you can, using this information, you can find what is wrong. Here everything is fine. So again, if we put the parameters to save the model in VTK files, we should have them. So let me look. So far we have only this output information, and inside databases we have VTK files. You see proc, number of core processor, and VS, VP, density. So you can plot again these files in ParaView. Basically, you will be plotting this figure. You can plot this figure, reproduce this figure. And the last step is to run the solver. Oh, sorry, it's too much. SPECFEM. The job is submitted, and let's look at the output again. It's not yet there. It will take 1 or 2 minutes to complete the simulation. So let's look quickly. This is important again, output information. You need to, what we can say, it's only 500 time steps solved at this point. I don't know, I don't remember how many exactly time steps. So So we put 2000 as well. About 30% is done for this moment. And if we specify in data parameter file the option to output the movie, which is the case here, you see the movie surface is equal to true, which means that the propagation of the field on the surface will be output in the output folder, and then we'll convert that files to the parview.inp files. Let's look again at the output solver. It's done. So we convert again. It was as we did in the first example. I just convert the output files to generate the movie for parview. So we select 2 here, then first time step, the last time step, using frame number, and for the norm of velocity. And the files are saved in the imp4.imp in the output file in this folder. So we can quickly play the movie. If I think I have this. So again, the mesh size is coarse. The frequency is, for this reason, the frequency content is relatively low, but you see the propagation in that mesh. So this is the second example. The main difference again is the way the mesh was designed. In this case, the external measure qubit was used, and we need to put this additional information for the qubit. And I'll go very quickly through the last example.